right? Here,
in such cases, okay, fixing the boundary is not equivalent to initial condition.
yeah, I think here he is just talking about on the spatial slice, right? On the spatial slice, the question is that between 2 points, there can be multiple geodesics, but because the distance scales that you are exploring, right, are much smaller than the curvature scale, right, the A0. That's what we discussed, right? The A0 is very big, right? It could even be infinite. Right? So because of this, right, locally we can just think of this as a normal Euclidean space, and then between 2 points there will be a unique geodesic.
In general, we in a second order differential, I think we say that we can either give two points, or we can give point and a velocity.
Yes,
at the same point.
that is true.
But this is not true when we have such special conditions.
Yeah, because the point is, in this case, what happens is that the coordinate system that you use breaks down. What you are saying is true, that if you can use the same coordinate system, right, then it shouldn't happen, because it's a second order differential equation. You put two conditions, that should be a unique solution. Okay. But on the sphere, right, if you try to set up this problem, then the coordinate system is not valid over the whole sphere. That's why you have this problem of having multiple geodesics. Exactly, that's right. But then this argument holds, right? Second order differential equation, two conditions, so it has to be a unique solution. Okay. So today we will basically analyze the equation that we derived last time, and we'll try to write all the equations in terms of the variable which is more natural, that's lambda of t, as a of t over a0. Okay, where a0 is a of t0, that's today. Okay. And in this variable, the Friedman equation this takes the form lambda dot over lambda square plus e over so a dot over a just becomes lambda dot over lambda. Okay, this is what we had in the Friedman equation. Then you had a k over a squared. That a squared I'm writing as a0 squared times lambda squared. And on this side, I have used the fact that the total row, okay, which was on the right hand side of the Friedman equation, is the sum of the three components: radiation, matter, and cosmological constant. Okay. And then you have separate conservation laws for each of the three components. So d dt of rho I lambda cube is minus 3 pi lambda dot lambda square. Okay, this equation was written in terms of a, but both sides have a factor of a0 cube that you can factor out, right? So once you write a as a0 times lambda, right? A0 of course is time independent. A0 is just a constant, so a0 cube factors out from both sides, and I've just cancelled it out. Is this clear? This is just a rewriting of the equations that we had found. Okay. So what is I? I here stands for matter, radiation, or cosmological constant. Okay, because you are imposing energy conservation, the T mu nu conservation separately for each component. Right? Cosmological constant will be automatic because G mu nu is conserved anyway. D mu G mu nu is 0. But you assume that matter and radiation have separate energy momentum conservation. Is this clear? Okay. So these will be the starting equations, and everything that we'll do in the rest of the course basically will follow from these equations. Okay, so it should be clear where these equations are coming from. Okay, these are just Einstein's equation together with some additional input which is that we assume that there is no exchange of energy between matter and radiation.
That is the basis of separating of this rho r plus rho m plus coulomb.
Well, this you can still write, even if these are time dependent, right? At any given instant of time, it's a sum of these two. But that is this decoupling of matter and radiation is the basis of this equation. Otherwise, you will have here the total rho and total p, right? The fact that you are demanding that this equation holds separately for matter and radiation. See, for cosmological constant, it will be automatic, right? This you can check, because if rho is equal to p, right, equal to constant, then this is an identity. Okay, rho equal to minus p. It is an identity. For cosmological constant, is a problem. But the fact that you are assuming that this is separately valid for rho r and m, right, is using this physical input. Then matter and radiation don't exchange energy.
This is valid in every approach. That is a statement.
No, it's not the statement. It's valid in the epoch that we'll be studying, right? In the early universe, right, the matter and radiation in some time was in equilibrium. Right? There you cannot use this equation, right, separately. Okay, you have to, so it's the sum of the two which will satisfy this. Okay? But you supplement it by saying that if the interaction was strong enough, then we set the T, the temperature of matter, equal to temperature of radiation. Okay, that will be the additional equation that we'll use. Right? If even that is not true, right? Suppose things are out of equilibrium, right? Then you have to do more hard work, right? You have to use transport equation to figure out how the energies are exchanged, and then put that in. Because it depends on a physical situation that what you should do here, right? And that you cannot get without using the physical input, right? Because that does affect how the universe evolves, right? How the energies are exchanged between matter and radiation. Okay, so first we'll try to solve these. Okay, in fact, solving these are easy. So first take matter. There we have the equation of state is Pm equal to 0. Right? Non-relativistic matter, we argued, has almost zero pressure. We set Pm equal to 0. And then we get ddt of rho m lambda cube equal to 0, which basically means rho m is equal to rho m naught by lambda of t cube. This is the time dependence of rho m. Not always means today. Is this clear? Because lambda is 1 today, right? At t equal to t naught, lambda is 1, right? So that sets the boundary condition of this differential equation. So this one, in fact, has a nice physical interpretation, right? This basically says that if you think of this as coming from a collection of particles, right, in a given co-moving volume, right? The number of particles in a given co-moving volume remains fixed, right? But that co-moving volume, right, expands. The actual physical size expands, right, by lambda. So the actual physical volume is lambda cube times the co-moving volume, right? And so the density correspondingly gets reduced, right? That's why it falls over as 1 over lambda cube. Is this clear? So for radiation, we have PR equal to rho r over 3. So ddt of rho r lambda cube equal to minus 3 times rho r over 3 lambda dot lambda square lambda dot is just d lambda dt. So this you can also write, it's a simple exercise, that this means d dt of rho r lambda to the 4 is 0. Okay, if we just write rho r lambda to the 4 as rho r lambda cube plus times lambda, right, and then do the distribution, right? d dt of rho r lambda cube will be given by this. The other one will be rho r lambda cube times d dt of lambda. Right? That exactly cancels this term. So this tells us that rho r of t is rho r naught over lambda t cube, lambda to the 4. Is it clear? So this also has an explanation. So what is the explanation of why is it 1 over lambda to the 4? Yeah, lambda of photons goes 1 over lambda cube. Yeah, because the photon energy gets shifted, right? Because the photon energy, right, is scaled by lambda, right? That's what we had said. Because frequency gets scaled by lambda, right? So the energy is proportional to frequency. Right? That's why it goes as 1 over lambda to the 4. You can also think of it from purely classical terms, right? You have this d dt of rho r lambda cube, and you have a minus sign here, right? So this right hand side is basically telling us that as the universe expands, right, if you photon in a given co-moving volume, right, that's working against the pressure, right? It has a positive pressure, so it's working against the pressure, and that's why you are losing energy, right? So the total energy is not fixed in a co-moving volume. If the total energy in a co-moving volume was fixed, then you do as 1 over lambda cube. But because of this expansion, it's working against pressure, right? Just like a expanding gas loses energy, right? Because it works against external pressure. That's another way of understanding why it's 1 over lambda to the 4. Well, that's a very, very vague thing here. Total energy is conserved in the sense that d mu t mu nu equal to 0, right? But because there is an asymptotic flat region, right? You cannot say that in that region it's like ordinary derivative of t mu nu equal to 0, right? That will be the standard conservation of total energy. So total energy conserved, yes, it is conserved in the sense that d mu t mu nu equal to 0, but that's all you can say. Yeah, otherwise you worry about where the energy is going, right? In fact, it's more puzzling for the cosmological constant, as you'll see, right? Because for cosmological constant, so let's do that also. Okay, here of course you already know the answer. Here T lambda is minus rho lambda. So we get d dt of rho lambda times lambda cube is equal to minus 3 rho lambda lambda dot lambda square. And this basically tells us that d rho lambda dt equal to 0. So rho lambda equal to constant. So if rho lambda is constant, that means the total energy inside a given co-moving volume is increasing, right? It grows as lambda cube. So you can ask where is the energy coming from, right? I mean, one way to explain it is by saying that because it has negative pressure, right? When it's expanding, it's actually gaining energy, right? When you work against positive pressure, you lose energy. When you work against negative pressure, you gain energy, right? That's one way of understanding where this why rho lambda is constant, right? So that rho lambda lambda cube is increasing, but it doesn't really give that much insight because you can ask where is the energy going, right? It's not going anywhere. It's just everywhere in the universe this is happening. Plus sign. Oh yeah, plus sign. Thank you. Yeah. So the energy is basically not going anywhere, right? This is what you get from energy mode of conservation. D mu t mu nu equal to 0. So now we substitute this here. Okay, to write this as a single equation for this variable lambda. Right.
So in the statements for some moving observer, they will perceive this data.
Yes, exactly. So for the co-moving observer, you will see that the energy density in matter and radiation are falling, but the cosmological constant remains fixed. Well, I can give a physical argument, but it will not satisfy you, right? A physical argument is that you are working against negative pressure because P is minus rho, right? Okay, so because you are working against negative pressure in a given co-moving volume, the total energy is actually increasing, right? And that's what is compensating for this loss of energy density because of the expansion. Oh, because for cosmological constant, P is minus rho, because the energy momentum density is proportional to G mu nu, right? And you saw that when it's proportional to G mu nu, if you work out, because rho is minus is proportional to G00, which has a negative sign, right? So the P and rho have opposite sign. No, I don't think there is any physical origin. This is what happens. If you want a general coordinate, if you want a fully covariant form of an energy momentum tensor, this is what you can get. See, any other form will break the symmetry, right? Like here, I mean, you don't have this. If you write G mu nu in the Einstein's equation, right? That's fully general coordinate invariant. If you write T mu nu of the form that you have written, right, that breaks the symmetry between time and space, right? So certain symmetries have been isometries have been broken, right? So if you want maximally isometric energy momentum tensor, then that's the only candidate we have. I mean, it's not that the general coordinate invariance is not true in this theory, right? It's just that the background that you have chosen, right, breaks certain isometries. Okay, so with this, we write the equation. I will now multiply this by lambda square. So lambda dot square plus K over A0 square is equal to 8 pi G over 3. So rho r went as 1 over lambda to the 4, right? So I can write rho r0 lambda square y0 over lambda square right? I just multiply by lambda square. So 1 over lambda to the 4 become 1 over lambda square, and 1 over lambda cube become 1 over lambda. So of course, this is a simple first order differential equation. You can solve it. Okay, at least numerically you can solve it, right? If you cannot solve it exactly. But what we'll do is try to get a physical insight into this, okay, without actually solving it. Okay, and to get a physical insight, we can write this equation in a slightly different way: half lambda dot square minus 4 pi G over 3 times rho r0 over lambda plus rho m0 lambda square Yes, fine. Just rewriting of the original equation. Now this we can think of is a classical point particle of unit mass potential E lambda, which is this whole thing, and total energy Is this clear? Because this is like a kinetic term, this is a potential term, so kinetic plus potential energy is equal to total energy. That's all we are using, right? One dimensional classical point particle. So we'll plot the potential in a few minutes. But we can look at this and ask what will be the acceleration of the particle. Acceleration is lambda double dot, right? Newton's equation. That we know is minus the gradient of the potential. Right? Acceleration is minus the gradient of the potential. So the minus sign will cancel this. So the acceleration lambda double dot, of course, it's trivial, you can just differentiate it and find it, right? But just from this classical analogy, right, we see the lambda double dot is equal to minus del V del lambda, which should be 4 pi g over 3 times minus 2 rho r naught over lambda cube minus rho m naught over lambda square plus 2 rho lambda naught lambda. Right? So now imagine what would happen if the cosmological constant was not there. If the cosmological constant is absent, right, then you see that both terms are negative. Right? So then this lambda should decelerate. And in fact, this is the reason why I said that when people first introduced this parameter Q0, right, which is essentially lambda double dot, right, they use a minus sign because they thought that it will decelerate, right, because nobody thought that there's a cosmological constant in the universe, right. So that's the reason why it was the Q naught was defined that way, okay? And this is the reason why it was a shock when people found that it's actually not, it's accelerating, right? It's not decelerating, it's accelerating, because that basically said that just using matter and radiation is not going to be possible to explain this, okay. And in fact, you can also check that any other equation of state, right, for which P is positive, the pressure is positive, cannot do it, right. Imagine that okay, it didn't work, so you say, okay, there may be another component of matter which you don't know, which has a different equation of state, right. P is some complicated function of rho, right. What you can show is that as long as P is positive, right, you'll always decelerate. Okay, I'll leave it to you to check this. So that basically showed that if you want to explain acceleration, you need negative pressure. Okay, and a natural source of negative pressure is the cosmological constant. Okay, is this clear? So let's plot V versus lambda. Okay, I'll plot it only for positive lambda. you see the metric is singular at lambda equal to 0, right? So you don't want to go beyond lambda equal to 0. Okay, so for positive lambda. Now you see that for small lambda, this term dominates, the radiation dominates. Okay, so this is the expression for V. 1 over lambda square is the dominant term for small lambda. Right? So it goes to minus infinity. So it goes like this. For large lambda, this one dominates. So it again goes to minus infinity. Right? And it remains negative all through. Right? Every term here is negative. So V of lambda is always negative. So the general shape is something like this. Is this clear? Reaching a maximum at some points here. And the energy minus k over 2a0 square. Okay, that's the energy of the particle. That we have already said that it's indistinguishable from 0, right? From experimental observation. So it may be positive or negative, we don't know, but it's very close to 0. Right? So the total energy may be somewhere here. Or here. Right? Or along the axis if k is really 0. Right? So this is the case when k is equal to minus 1. This is the case when k is equal to 1. And this is the k equal to 0 case. Right? So this is the energy, total energy in the same plot. Now today lambda is equal to 1, right? That's the way you have chosen it. Roughly, that corresponds to what kind of point on this graph? On this side or that side? Which side? This side. Any other opinion? Well, the only other opinion is on the other side, but you have to justify why this side or that side, right? Okay, so why this side? Yeah, so it's yes.
Minus del V by del lambda should be del V by del lambda should be.
Yeah, because see, it's accelerating, which means that the lambda dot is increasing, right? So lambda dot can only increase at the cost if V is lowering. Okay? Because lambda dot square plus V is constant, right? That is the kinetic energy, the kinetic plus potential energy. Half lambda dot square plus V is constant. So if lambda dot has to increase, then V better decrease. Right? That's another way of saying that acceleration, you don't even have to differentiate V, right? You know, if lambda dot is increasing, V should decrease because lambda dot square plus half lambda dot square plus V is fixed, right? So you must be somewhere here. This one, okay. So we are asking whether we have plotted this V, right? And lambda equal to 1, that is today, is somewhere on this graph, and we are asking where it is, right? Now, here we are using the insight that today we know that lambda double dot is positive. Universe is accelerating, right? Now imagine a particle moving under this potential, right? So what will happen? The particle is climbing up the potential, right? When the particle is climbing up the potential, it is decelerating, right? So if it's accelerating, that means it must be climbing down, right? So it must be on that side, right? And because we know that today we are accelerating, right? We must be on this side of the potential of the maximum. Is clear? Any other question? Oh, these are the right hand side. These are total energy, right? I am also plotting the total energy in this plot. Yeah, lambda dot can never become 0. From this graph, you can see lambda dot can never become 0 because this height, because it is close to 0, right, and the potential is always negative, right? It will always be remain positive. It can never become 0. Because I've drawn it like this because V of lambda is to a negative, right? All through. But A0 you already know is very large. K over A0 square is indistinguishable from 0 today, right? So it must be very close to the origin, to the that axis. Is it clear? So from this picture we see that this K really doesn't affect anything. Right? It's not affecting us today. It will not affect us in the future or the past, right? Because we can see also from this picture, right? That today we know that this is smaller than this on the right hand side. Yeah, in fact, we can show that at least this is smaller than both this and this. Okay, lambda equal to 1, right? So these are like 0.3 and 0.7 of the total. Okay, that we'll discuss in a few minutes. Okay. But this term is smaller than both this and this today. In the future, okay, this term is going to grow. Right? This is remaining fixed, right? This doesn't depend on lambda. So in the future, this term will always dominate, will be much larger than the K over A0 square term. Because today it's already much larger than the K over A0 square term, right? So in the future, this will always dominate. In the past, this will dominate because today lambda is equal to 1, right? When lambda was smaller, right, this will be much larger. This remains fixed, right? So this will dominate over K over A0 square. So K over A0 square really doesn't affect anything in our evolution, right? Neither in the past nor in the future. Is this point clear? Spatial geometry, yes.
But that is not playing any sort of role.
It just so happens that this A0 is so big, right?
So we cannot simply distinguish between any of them.
Exactly, right? And but what is more important is we cannot distinguish today, that is clear, right? But you also cannot distinguish in the future or the past. Because of this fact that one or the other term will always remain much larger than K over A0 square. That either this one, in the future, this one will remain much larger than K over A0 square. In the past, this will remain much larger than K over A0 square. So neither in the future nor in the past, right, this term will have any significance. Is it clear? Okay. But this was not the case when I was studying cosmology, when I was in the graduate school. Okay, there the value of K, right, the sign of K was a life and death question. Okay, so let me explain why, right? Because at that time we didn't know about cosmological constant, right? So everyone thought rho lambda is 0. So let's suppose rho lambda is 0, right? And plot this again and see how the plot should be. If rho lambda is 0, then this term is not there. For small lambda, it still goes to minus infinity. But as lambda goes to infinity, you can see this goes to 0. Right? So the plot will be like this. So asymptotically approaches this line. Okay. So now let's look at these two cases. This is K equal to 1, sorry, K equal to minus 1, this is K equal to 1. K equal to 0 will be along this. So how will the universe evolve for K equal to 1? For K equal to 1, for suppose, sorry, K equal to minus 1, K equal to minus 1, this is a positive energy. Yeah, so how will it evolve? lambda at all will become just constant. Yes, that's true. But it will remain non-zero. It's like if you take a particle and throw it with energy which is positive, right? Positive energy, it will just escape. Is that clear? So if energy is positive, right, then lambda dot never vanishes. If this side is positive, right, then lambda dot is positive number plus this. It will never vanish. But it's also visible from here. Right? That the potential always remains lower than a kinetic energy, right? So lambda dot never vanishes. In this case, what will happen? It will truncate. It will just stop evolving. The universe will stop evolving. Wait, but okay, let's see how the motion will be. Lambda is increasing, right? We start from here. At that point, lambda dot will become 0. Then what happens? Then it will, well, it can become imaginary. If lambda increases. That's a turning point. See, it's like if you take a particle and throw it up, right? But with a velocity which is less than the escape velocity, right? What will happen? It's exactly the same problem, right? I mean, see, this is somewhat of a extra term, but for large lambda, it's basically this term which is the potential, right? Inverse 1 over r potential. Right? That we know what happens, right? In 1 over r potential, if you throw a particle radially out, right? If the energy is negative, if the total energy is negative, it will go some distance and then come back, right? If the energy is positive, then it will just go, right? It will escape the potential. Okay? So here, what will happen is that as it comes here, lambda dot will become 0. After it will start turning back. Right? And lambda will start decreasing, and eventually it will go to 0. Right? So that was a big crunch, right? So the point is that you can see in this case, right, whether k equal to -1 or k equal to 1 made a lot of difference about the future of the universe. Right? Whether the universe will collapse back into a point, or whether it will continue to increase, continue to expand. And in this case, we have to do a little more analysis, but one can show that in this case it also escapes. It's like a parabolic orbit. So you know it in inverse square potential, right? Sorry, inverse square force, which is potential is 1 over r. Right? If the energy is exactly 0, then you have parabolic orbit, right? Which keeps going, right? Which doesn't turn back. So that will be the case for k equal to 0. Because for k equal to 0 and -1 would be safe, the universe will continue to expand, but for k equal to 1, the universe will collapse back to 0 size. Okay, but because of the cosmological constant, that is irrelevant today. Right? Today, irrespective of the value of k, universe will continue to expand.
So to explain this Hubble expansion,
no, they use k equal to k over a0 square is small anyway, right? So they use the fact that we are somewhere here, right? So it doesn't really matter. Okay, so not here, we are somewhere here. Right? So this is very small anyway, right? So as long as you are here, you don't see the distinction. Right? You are still decelerating. Right? I mean, that's why if we knew that we are not decelerating, then there would be a problem, right? But that we didn't know. Right? So okay, everyone thought the universe will be decelerating, and we are going, right? And eventually we may turn back, right, in the far future. But we don't know, right? That depends on the value of. But explaining the Hubble expansion was not a problem, because as long as you are in this branch, right, when it's still increasing, you can explain Hubble expansion. Exactly, if they're not aware of acceleration. Okay. Yes.
A-note is coming from the fact that we are the entire observation that today the current.
Yes.
Some say we are doing all these calculations very
Yes.
Not so big. And at that time, we will be able to distinguish between all these.
No, will not be, because that's what this argument says. See, A naught by definition is A today, right? What you are asking is that is it possible that in the far past, right, this term would dominate, right? A naught is A naught, right? A naught is today's A naught. But you can ask if in the far past this term will dominate. Okay? And the point is that in the far past, you see that these terms become larger, right? This remains constant, this becomes larger. Right? So in the far past, this will not never dominate. Right? In the far future, it could dominate if the cosmological constant was 0. But in the far past, the effect of this term would have been even smaller, right? Because these terms would have been larger. Any other question?
So that negative question.
Yes.
Are there any considerations like quantum?
Yeah, it's basically a term in the Einstein's equation, right? So if you have a scalar field potential, for example, right? A scalar field V of phi with a minimum at phi naught, right? And if V of phi naught is non-zero, this produces a cosmological constant, right? Because there is if you remember the term in the Lagrangian, in integral d4x square root of minus determinant g. Okay, there are kinetic terms, but the potential term comes like this, right? With a minus sign. Okay. So if V of phi naught is non-zero, right, and this acts as a cosmological constant. Right? So that's the explanation. So in quantum field theory, there is a explanation of the cosmological constant. Right? What is not explained is why is it so small, right? Because in quantum field theory, normally the scales that you deal with, right? The energy scales are huge, right? Imagine that standard model scale, right? GeV to the 4, right? That's huge compared to what you observe today, the value of the cosmological constant. Right? So the point is, when people thought that the cosmological constant is 0, right? There is no good reason, right? The only reason was that, I mean, in quantum field theory, the natural value of the cosmological constant would have been much larger, right? And so that couldn't be explained. Why? I mean, even if people knew that even if there is cosmological constant, it was very, very small, right? Because of course they are bound. So people knew that the cosmological constant is not is very small even if it's there, right? And then they basically thought that okay, if it's so small, there was some symmetry reason why it's so small, even though you don't know what the symmetry reason is. And if there is a symmetry reason, then it must be 0. Yeah, so that was the kind of argument that people used to say that cosmological constant must be 0. But in quantum field theory, certainly there is scope for cosmological constant.
So this they always construct some potential this non-zero.
Yes.
So what is quantum about it? What exactly?
Well, okay. In ultimately, it's a quantum corrected potential that you have to deal with. Okay? Even if you start with a scalar potential, right? There are quantum corrections to this. You have to include all of those. Effective potential, exactly. That's right.
This is somewhat after symmetry.
Well, even before symmetry breaking, nobody can prevent you from writing V of phi, which is there's a phi square and phi 4 term, and then there's a constant term. Right? See, in quantum field theory, that constant term has no relevance. But once you couple it to gravity, right, then the constant term also has relevance, right? Because that's what acts as a cosmological constant. Of A naught. Oh, you don't know, it could be infinity also. See, because you have not detected it, right? That you can figure out. That you can figure out because I'll give you the values of these. Yeah. Yeah, but it could be 0. It's the point as far as experiment is concerned, it's indistinguishable from 0. Right? Because no experiment has shown any non-zero value of k over a0 square. Well, one way to measure it by using this equation, right? If you calculate lambda as a function of t, right, it will certainly depend on this k over a0 square, right? And by solving that, you can calculate k over a0 square. Yeah, there are various other ways of doing it, right? But this is one. Right? All of those, if you know lambda as a function of t, if you have enough data points, right, you can determine all of those just from lambda as a function of t, right? Yeah, these are initial conditions, but suppose you know actual value of lambda as a function of t, right? Then you know these initial conditions. See, lambda is a function, right? These initial conditions are all related to say derivatives of lambda, various derivatives of lambda, right? If you calculate lambda, lambda dot, lambda double dot, lambda triple dot, they will all depend on these combinations of these. So if you know enough information about lambda, you can determine all of these. Because the function has infinite number of information, right? Here you are only talking about a finite number, right? These 3 numbers plus this 4 numbers, right? So you can certainly determine 4 numbers if you have one whole function. So we'll see how these are determined. Okay, not all of them will use lambda, but some of them will.
All this rho r0, rho x0, then we will look at the nearby galaxies and nearby.
Exactly. Yeah. Okay, I'll just discuss in a minute how we determine these. Yes.
We are doing it on a third space, and we don't exactly know the space because we don't know that.
Yes.
So the calculation will require. So the calculation will depend on lambda, and the geometry will also depend on the lambda.
Yeah, but you don't probably the way you do it, you don't do it on lambda. You do it on a general metric, right? And then evaluate it in the particular background that where you want to evaluate. Right? Effective potentials are always like that, right? You evaluate it in any background that you like, right? And then you use it to use it for other backgrounds. Yeah, so you can do the calculation in flat background and then use it to say what happens in a curved background. It's like if you have a v of phi, right? If you know how to calculate, if you know the functional form near phi equal to 0, all Taylor series expansion, then you know the function. And you can reconstruct it and you can find the value of the function at a minimum which is far away. Right? Here, in fact, it's a much simpler problem because this expanding universe, right, is not very far from Minkowski space. The expansion is so slow, but after all, we approximate our neighborhood by Minkowski space, right? And that's because lambda dot is really small for us. And lambda changes, right? Once in 10 to the 10 years. It becomes double the size in 10 to the 10 years. Right? So lambda dot is really small, so it's as if we are in Minkowski space.
But then that calculation will not have any information about the background.
No, after you do the calculation, then you evaluate in the background geometry. The square root of minus determinant G will know about the background geometry, right? The effective potentials are always calculated like that. Right? Otherwise, I mean, why would you use effective potential, right? In every background, you have to do the calculation again, right? Then you don't need, you don't use the language of effective potential in that case, right? It's like normally we calculate the effective potential in QED and then use it to calculate, for example, the hydrogen atom, right? You don't calculate it again in the presence of hydrogen atom. Okay, so let me write this equation again. Lambda dot square. Okay, I'll write it as minus 8 pi G over 3. This is just various ways of writing this. Rho r 0 over lambda square plus rho m 0 over lambda. Okay, this is the same equation. Now, at t equal to 3 naught, that is today, lambda equal to 1 and lambda dot equal to h naught. That's the definition of the Hubble constant, right? So, when we apply it on this, we get h0 square as minus 8 pi G over 3 okay, so I'll write this also as 1 minus 8 pi G. Okay, let me just define so that I can just avoid one step. So we'll define rho C, okay, which is called the critical density, as 380 square over 8 pi G. This is the definition. Okay, because this is a dimension of density. That's why we call it critical density. So if you do that and then if you divide this equation by h0 square, right, you can write this equation as 1 over 1 minus 1 over rho C right? So you see from here that this is rho total. That is rho total today, total energy density today. So if rho C is larger than rho total, then this is less than 1. Right? So the left hand side is positive. If the left hand side is positive, that means K must be equal to minus 1. And you can determine H0. Right? Because whatever that left hand side is, right, it's negative, right? So it's 1 over H0 square, H0 square is that negative number. Is that my negative of the negative number, right? Which of course positive. So you see already that we have a determination of A0, right? This equation can determine A0. if you calculate rho c is of course some number, right? H0 is measurable, rho c is some number. If you can measure these, some of these, and compare with whether this is less than rho c or larger than rho c, you can determine whether k is equal to 1 or minus 1, and you can determine A0. So this is, if it's less than rho total, then A equal to 1, and if it's equal to 0, but if it's equal to rho total, then k is equal to 0. But this, of course, you can never be sure, right? I mean, in experiment, when you measure something, right, you can never be sure that it's exactly equal to something, right? So you can never say whether k is 0 or not. All you can do is to put bounds on A0. Okay. So when I said that A0 today we cannot distinguish, right? A0 is large enough. That translates to this fact that in today's observation, rho c is, or rho total equal to rho c within experimental error. Okay, but of course that brings us to the question, how do you know what rho total is, right? We have to know how to calculate these, rho r0, rho m0, and rho lambda 0, right? If we know, then this makes sense. Okay, so what in the rest of this today's lecture, I'll explain how to measure those quantities. Okay, how those are measured, rho r0, rho m0, and rho lambda 0. Is this clear? Are there questions? Oh, maybe I should also give some numbers. Okay, so H0, okay, that is the current value, is of the order of 70 kilometer per second per megaparsec. Okay, a parsec is about 3 light years, I think. As far as I remember, we can look up the exact number. Okay. Which basically means that if we observe galaxies at a distance of a megaparsec, okay, then on the average, those galaxies are moving away from us at a speed of 70 kilometers per second. Okay, that's what we'll see today. Is this clear? See, H0 has a dimension of inverse time, right? 1 over, because H0 is lambda dot, basically, today, right? And this also has dimension of inverse time, even though I have written it in this way, right? Because the 70 kilometer and megaparsec are both dimensions of length, both lengths, right? It's just that, I mean, it's easier to write it this way because this tells us physically what you should observe. Okay, that if you observe galaxies at a distance of a megaparsec, on the average they'll move away from us at this rate. Okay, so based on this number H0, right, the critical density rho c, which is given here, this is about 6 protons per meter cube. Yeah, the substitute is H0 value, right? You can write it in terms of gram per meter cube, but this is, I mean, it makes it clear how small it is, right? Yeah, 6 proton masses per meter cube. Okay, on the average, this is the critical density, right? Okay, so now let's try to see how to calculate this. How we determine these individually, rho r0, rho m0, and rho lambda 0. Or maybe I should also include something else. Okay, so we define omega I as rho I0 over rho C. Okay, so I stands for R, M, or lambda. Because instead of giving the actual values of the rho, right, we give the ratio of the rho to critical density. Right? Because critical density you already know. It's 6 protons per meter cube, right? This number. So it's physically it's more useful to give the ratio of the actual observed density to the critical density. Okay, so omega r actually is the easiest. So omega r comes from the cosmic microwave background radiation, right? That's the radiation we are talking about. So cosmic microwave background radiation, CMBR, has T equal to 2.73 Kelvin. So once you have the temperature, you can calculate energy density, right? That's Planck's distribution formula tells you what the energy density is. So rho r naught is AT to the 4 for some constant, known constant. And this gives you omega r naught of the order of 10 to the minus 4. So the ratio of the actual energy density of radiation to the critical density is of order 10 to the minus 4. Is this clear? Yeah, but those radiations are the energy that they carry is very, very small. The CMBR, the temperature is low, right? But it fills the whole entire universe. Average density, right? So those stars that you see, right, which are localized inside galaxies, right? The amount of light that they emit, and if you calculate the energy density, that's much smaller.
So we have to divide that energy with the
average volume, right? Or the total volume. Most of the universe, right? There are no galaxies, right? It's empty. So those will go in the denominator. No, today it's 2.73 K. Right? Long time ago, temperature was higher. Right? Today what we observe is 2.73 K. Exactly, that's right. I mean, we don't have to look far away. We can put our detector here and you see what radiation is coming to us, right? And because of the homogeneity, the same detector placed elsewhere will also have the same radiation coming, right? At least at this particular cosmic time. Yeah, and that temperature is 2.73 Kelvin.
When we say rho r0, this is the current approach of what we are. And current approach means we should not look like very, very far, because when we look very, very far, that means
we have to correct for it. We have to correct for it. We can look very, very far. We know the red shift, right? So you have to correct for that red shift. So that you have to do always, right? Whenever you look very far, you have to correct for the red shift. Okay, now let's go to the matter part. But those are even, I mean, insignificant. There are chances of gravitational waves coming from early universe, but those energy that they carry is really, really small. Now, one point you can see already that even if this is very small today, right? This rho net not contribution is small because omega r naught is small, right? In the past, when lambda was smaller, this is going to be the dominant term, right? So how far in past you have to go depends on how small omega r naught is, right? But at some point in the past, this is going to be the dominant term.
Can we use that?
We will determine the age of the universe. Yeah, we'll use it, but we don't really need that part, right? Most of the age of the universe comes in the from the part where matter dominates, right? Matter and cosmological constant dominate. So you don't, the correction due to CM that epoch is so small that you don't have to worry. But of course, that's needed for various other things. We are now going backwards, right? I mean, the correct way to explain the universe will be to start from early universe and then see what happens when you evolve forward, right? But right now, we only have the data today, right? You have to reconstruct what happened earlier in the early universe from here. Right? But once you understand that, then eventually you have to start from there and evolve forward. So omega m, this is in fact the most tricky part. That the naive way you will calculate omega m0, right? You will just estimate that nearby galaxies, how many galaxies there are in a given volume, right? How many stars are there, what are their masses, add them up, divide by the volume. Right? That's the way it is typically estimated. And if you do that estimation, right, then you get a number which I'll call omega b. Omega b stands for baryons, right? Because most of the observed matter is what we call baryons, right? Protons and neutrons. Because all the nuclei are made of protons and neutrons. Right? Electrons are very little mass compared to protons and neutrons. So this number turns out to be of the order of 0.04. More than the than radiation, but still small. However, there is evidence that this is not all the matter that we have in the universe. Right? There is additional matter which I'm calling matter because they also have p equal to 0. Okay, or p close to 0, so they're non-relativistic. Okay, but they are present. Okay, and there are various experiments that show the presence of these matters. Right, the first kind of analysis that was done to actually predict this, okay, is what is called a galaxy rotation curve, right? So let me just describe that. But there are many different ways, different experiments, right, that has been used to show that there must be dark matter. So the galaxy rotation curve the idea is the following. Suppose you have a galaxy. Okay, which of course has a distribution of stars. And you examine stars which are near the edge of the galaxy, okay, far away from the center. Okay, so that most of the mass of the galaxy would have been inside the, if you draw a sphere of radius that contains that star, most of the mass would have been inside. In that case, we can find the motion of the star, right? Imagine that it's moving in a circular orbit. You just apply the standard non-relativistic formula. These are moving slowly, right? They're at the edge of the galaxy. So mv square over r is centrifugal force is g m over r square. Sorry, this is small mv square. Okay, so m is the mass of the star. This is the mass of the galaxy. And r is the distance from the center. Okay, they are just balancing the centrifugal force with the attractive force due to gravity. So this will tell us that V goes as square root of Gm over R. Right? So if you plot V versus R, right, you look at various stars near the edge of the galaxy. And if you plot V versus R, then for near the edge, it should fall off as 1 over square root of R. What one finds instead that it goes like this. Okay, further away you go, the velocity remains the same. Is this clear? So if this is the case, right, then what does it mean? That means that M must be proportional to R, right? The total mass of the effective mass of the galaxy, right, which is the mass that is contained inside the sphere of radius R, right, is not decreasing, but it's proportional to R. Right? So the density is falling, right? Because if the density was constant, it would go as R cube. So the density of matter is falling near the edge of the galaxy, but where you think that all the visible, most of the visible matter is inside already, right? It is not the case, right? Because the farther away you go, you still see the same velocity. So this basically tells us that there must be extra matter that is contained in the galaxy, and that extra matter is not visible. It's not in the form of stars and planets and so on. Now, then there are various possibilities. Maybe the extra matter is some big planets, Jupiter-like planets, which are not visible, right? Which do not have their own light and so on. But there are various ways to rule such things out, okay, based on early universe cosmology. And the most likely candidate that is, at least today, the most likely accepted candidate is that these are some extra elementary particles that you haven't seen, right? Some weakly interacting elementary particles which are filling the universe. And their density can be estimated based on this galaxy rotation curve and various other experiments. Right? It's not just one experiment, it's a combination of many experiments that can be used to estimate the density. It's a weak interaction scale, right? Weak interaction scale or less. Because people are doing, I mean, the way you know it is because there's a lot of high energy physics experiments that are going on, right? If this dark matter was interacting, right, then they will interact and produce some new particles, which you may observe in today's experiment. So using those, you put bounds on how strong the interaction between the dark matter should be. And what you know that it's weak interaction scale. At least it should be less than the weak interaction strength.
You observe for all sort of galaxies.
Yeah, for all sort of galaxies. There is also a direct observation based on bullet cluster, right, which I'll not describe, but it's basically two galaxies which are passing through each other, right? And you see that the gravitational profile, right? You can look at the gravitational profile of those galaxies, right? And the electromagnetic profile, right? The radiation that is coming out. Okay? And you see that the radiation is coming out mostly from some region near the core, near the center, but the gravitational profile is far extended. Okay? And so the current understanding is that dark matter, because they are non-interacting, right? They are more or less passing through each other, right? So they have extended far outside. But because the ordinary matter is more interacting, right? There's electromagnetic interaction. They collide, and then there's friction, right? Which slows down the ordinary matter. So when two galaxies collide, what happens? The dark matter goes faster. Ordinary matter, because of the friction, gets slowed down. Okay, so if you look up bullet cluster, you will find the full experiment, right? What exactly is observed. So that's also thought of as an evidence for dark matter. So from all these experiments, what we know is that omega m0 is of the order of 0.3. you see that most of the matter is dark matter, right? The baryon is 0.04, right? Rest is dark matter among whatever matter you see we have in the universe. Okay, so and then rho lambda naught, once you get this, omega lambda naught or rho lambda naught is calculated from deceleration parameter. So for this, let's just look at the equation again and write this equation as lambda dot square as which I'll write as h naught square. See, this is 1 over OC, right? So times omega r naught by lambda square plus omega m naught by lambda plus omega lambda naught lambda square. Okay. It's just a rewriting of the same equation. So if we now take the derivative of this, so d dt of this, that gives you 2 lambda dot lambda double dot is equal to h naught square times minus 2 omega r naught by lambda cube minus omega m naught by lambda square plus 2 omega lambda naught lambda times lambda dot, because you are taking the derivative with respect to t. So there's a lambda dot. It comes out just. So lambda double dot half h naught square times, okay, so this today at t equal to t naught. Lambda double dot is, so this lambda dot and that cancels, half h naught square times today lambda is 1, right? So I can set all of this to 1. So minus 2 omega r naught minus omega m naught plus 2 omega lambda naught. Is clear? I just cancel lambda dot and set lambda equal to 1. But now recall the definition of the deceleration parameter. We had taken lambda of t as h naught times t minus t naught minus half q naught h naught square t minus t naught square and so on, right? Higher order terms. So lambda double dot at t equal to t naught is basically minus q naught h naught square. So compare these two. tells us that minus q naught is minus half times minus 2 omega r naught minus omega m naught plus 2 omega lambda naught. Last half, yes, thank you. Last half. Okay. So now we discussed our last time how to measure q naught, right? From this distance redshift relation. Okay. This is known, this is known. Right? So this determines lambda naught, omega lambda naught. Okay. So this gives omega lambda naught. Okay, this is minor. I have written minus q naught, but q naught is negative, right? As we discussed. Right? So omega lambda naught is positive from this. And you see now that omega m naught plus omega lambda naught plus omega r naught is nearly equal to 1. Right? With experimental accuracy, it's equal to 1. And that's what we need, right? That's what tells us that A0 must be very large. Okay? Because total energy density today should be the critical energy density, right? For A0 to be very large. That means the total omega, sum of all the omegas, should be equal to 1. Right? And what we are saying is that with our current experimental understanding, the sum of these 3 omegas is indistinguishable from 1. Right? Which means sum of the 3 densities is indistinguishable from critical density. Yes.
We need to use the distance redshift.
Yes.
That distance redshift relation itself is dependent on not its sunsets because it is dependent on how the universe slices are.
True, yes. So, yeah, but we discussed that, right? We wrote down the algorithm. Right? So
find out D as a function.
Yes.
We need to make some assumptions.
But that again you can do iteratively, right? So it's one experiment, one unknown, right? So you determine it. So number of experimental results, as long as the number of experimental results is the same as number of unknowns, right? You can determine it, right? All you are saying is that maybe you have to do a little more work.
That's fine. But I'm saying that the measurement still depends on the.
True. So it's a nested measurement, right? But nevertheless, as long as you have the number of data points is the same as the number of unknowns, you solve for those, right? See that the part that requires k, right, was not that the distance redshift. Distance redshift didn't depend on k. Right? What depended on the how to measure the distance. Right? We said that you take the luminosity, to construct the distance from luminosity, you may need the k. Right? Because luminosity you spread out over a certain distance, right? And then they have to calculate the area, right? And you have to divide. That area will depend on A0. Right? So if you don't want to set A0 equal to large there, you take finite A0, right? You will get a nested relation. But at the end, you have the number of data points is the same as the number of variables, right? So you can say, okay, you postulate A0 equal to infinity, you calculate this and then you verify that A0 equal to infinity. Right? That's another way of stating this. Yeah, your assumption that A0 was big is consistent because this is saying that A0 is big. Is this okay? Right. So from tomorrow then, Right? This will be the key equation that we'll try to analyze. Not tomorrow, next week. Lambda dot square is this. Because here now everything is known. H naught we know, right? In fact, H naught will be the overall scale quantity that will set the time scale, right? Because H naught has a dimension of inverse time. Right? All of the other quantities are dimensionless. Right? This is 10 to the minus 4. This is 0.3. This is 0.7. Yeah, so this will basically set the overall time scale, and then we can work with this, right? In fact, you can just eliminate H naught also by redefining T by scaling T by H naught, right? Because this is ddt d lambda dt, right? So H naught times T, if you define a new time, right, then H naught also disappears from this equation. So you can see the age of the universe, right? You just evolve this backward. Our age of the universe will be the time when lambda was 0, that will call T equal to 0. Right? And then by integrating that equation forward, we will determine what is C naught. Today lambda equal to 1 at T equal to naught by definition. Right? And we say that lambda equal to 0 at T equal to 0. Right? So we just integrate that equation to figure out what the age of the universe is. Right? And the various other quantities also will come out from this same analysis. Right? Questions like how far we can see, right? How far we will be able to go, and so on. Okay, I think I'll stop here. Yes. Yes.
Basically, now it starts. This is the idea of.
Exactly. Yeah. That in the early universe, the lambda was very small, right? I mean, if it's really 0, of course, you cannot trust our equation, right? Because then the curvature becomes infinite. But we start from a place where it's small enough. Okay, so that's you can call the Big Bang. The point is, physics of that part, right, is not used in determining the age of the universe, right? Because the age you determine from because that interval is very small, right? Things are happening very fast at that time, right? So as you will see, the age basically is determined by the matter dominant part of the universe.
You will divide by some distance. Is the size of the.
Yes.
What scale will be divided?
Say we take a big scale, right, of the order of 100 megaparsec. I think that's the kind of I have to check up the details, but it's a huge scale, right, which has many galaxies. Okay, that's the distance scale over which you average. Right, so the universe becomes homogeneous and isotropic over certain scales, right? So it's that scale that you have to use to average.
I don't know. I'm not quite sure about this, but in GW it concludes that this gravitational waves carry a lot of 450 energy, but coupling with matter is very small.
Yeah, but those energies are very localized, no? See, imagine that it cannot carry the amount of energy that is more than the mass of the black holes, right? So you take whole mass of the black hole, right? That's just one star out of this whole galaxy, right? So compared to the size of the galaxy which is contributing to the matter density, that is extremely tiny. Right? Even if the all the energy is getting converted to gravitational waves. How did CMB get? Well, we will see. I mean, maybe we will not see in this course. In the early universe, right? I mean, basically, according to inflation, the rolling of a scalar field produces this energy, right? Which you see today as CMB.
It's some symmetry breaking potential.
Well, it need not be symmetry breaking, but some potential of a scalar field. Yeah? Maybe in the last week we may discuss a little of this.
This is a little bit away from. So, yeah, but from symmetry arguments, from observation, came to the form of the matrix, the cosmological matrix. let's say for if you want to look at the quantum of the part of this, so should you only integrate over these cosmological metrics, or should we consider all metrics?
No, all metrics.
All metrics.
Yeah, yeah. This is a background, right? Fluctuations will involve everything.
I've seen some calculations where people only integrate over that lambda t.
No, but that's because it's hard to do calculation over everything, right? So you try to simplify things, but actual calculation will involve everything.
Keeping those backgrounds.
Yeah, treating this as background.